Good to be here. It's the first seminar of the year, first BIOS seminar of the year. A lot of you have been to these before and been a part of them. Some of you have not. So I'll give a brief background on what we are and what we're doing. My name is Pete Miller. I'm a professor on campus, and I work along with Maria, who is our associate director of BIOS. With BIOS, which stands for Badger Inquiry on Sport. It's an effort we have to bring research together in the area of sport across many disciplines. So we, over the last couple of years, have hosted a bunch of different scholars who study sport from different angles. How do you apply different disciplines, different tools and instruments and methods to more deeply learn about sport? We hope to do that both to benefit our scholars, to give our scholars place to do great work, but also to benefit our department here where we are. If you look around the walls, this is called Heritage Hall, and it shows kind of the history of Badger athletics in all these different areas. And just looking at just the pictures are kind of a cool way to get a really quick sense for the diversity of stuff that happens in this department. Everyone's here for the football game tomorrow, which is going to be an awesome event, but there are 23 teams here in this unit, and each and every one of them has a history, each of them has a story. And so we're trying to learn about each of those sports in many different ways. So that's what we do in BIOS. We bring that all together. We have some very specific ways we do that. And you're always welcome to join these in the weeks ahead. We have a slate of seminars throughout the academic year. So you're always welcome to join and to learn more. You can contact Maria with any questions about that. Mm-hmm. Today we're excited. Hi, Sarah. Today we're excited for our first seminar of the year. And Professor Samir is here to share some of his really interesting work in statistics. And he applies in very different and interesting ways than we've had before in BIOS. He was very kind and generous to speak at our symposium this summer. We had about 150 or 200 coaches here from all around the state in Camp Randall Stadium. It was a great event. And at that event, Samir talked with a panel about how can we think about data in different ways in athletics? How can both researchers, but also like coaches, athletes, and others make better sense of what they're doing by thinking about data in smarter ways? So today, Samir will talk a bit about some of his research, but also the bigger picture about data and sport. So I want to welcome Samir, who's a professor in statistics here on campus, to this seminar, and thank him, and thank you all for being here. Thank you.
So thanks, everybody. Can you all hear me? Or okay? So this is really I'm really excited to share some of my work here today, and it'll be about baseball, and it's a project that I did back when I was a graduate student, and it just has sort of been a constant source of inspiration and new developments. And I'm going to keep the talk. The sort of the technical bits of the talk fairly, we're going to stay at a high level here. But what I really want to emphasize is, there's a lot of data floating around sports right now, and a lot of interest in how do we use data and what sort of insights we can gain from data. And as a statistician and as sort of an applied statistician, I think really the questions we should be asking is not so much what is the data going to tell us about our sport and about our practice, but really thinking about what questions do you want to know about your practice, and can data help you answer them? So really centering the sport and centering the subject matter expertise rather than collecting data for the sake of collecting, because the data by itself isn't going to save. It's not going to tell you anything. There's a phrase people like to throw around, like letting the data speak for itself. But no matter how many times I hold my ear up to my spreadsheet, the data never says anything to me. So you have to ask good questions. And I think this particular project was kind of the first time I really understood that it really matters what questions we start with, and then can we use some of the statistical tools that sort of I trained with to help answer those questions. And so to do that, I'm going to start with a picture, and I apologize for the sort of potato quality of them. In old versions of the talk, I used to use like cell phone pictures of the game that I took. But then I found yesterday like an actual screen grab. So this was the 2015 AL wildcard game. So this was between the Yankees and the Astros. This was a little bit before the sort of banging on the trash can era of the Astros, but they were sort of close there. And what's happening here is if you can see the ball, there's the ball right there, and there's the ball right there. And what Fox did in their broadcast was they overlay kind of a strike zone. So right in baseball, we know that the batter doesn't have to swing at every pitch. If they don't swing and the ball passes through the strike zone, the umpire is supposed to call it a strike. If it passes outside of that strike zone, it's supposed to be a ball. And if you watch, I don't know, maybe one inning of baseball, you'll know that umpires don't follow that rule at all. Strike and ball decisions are super volatile. They're not consistent umpire to umpire. They're not even consistent player to player. That being said, here are two pitches. By rule, they both missed the strike zone, so the umpire should have called them both a ball. And you'll see that they're like fairly similar. They're both missing the batter on sort of the outside edge of the strike zone, down and away. But if you look at this picture a little bit more, it turns out that this pitch over here on the left, this was a ball. And the pitch over here on the right was called a strike. And so I want you to take a few seconds to just kind of look at this picture. There's a lot of information here. I've given you kind of the score, the inning, the base runners, the outs, the pitch count. There's obviously different players involved. And I kind of want to know what's driving the difference in the call here. Yeah.
The right one's the left-handed pitcher, so the ball's probably turned. That's the right.
Right. So probably the umpire is saying, oh, it's coming towards me. It's probably going to go through the zone. And okay, it's the handedness of the pitcher is probably at play. What else is there?
So the catcher behind the plate. Or a bit more student.
Yeah, so let me see if I can rephrase that slightly. Basically, this player right here is super compact. He's not getting out of his stance, whereas he's almost looking like he has to reach for it. So that might make the umpire think, oh, he's chasing it. It must be outside of the zone. What else is there? Yeah. Yeah, it's a little bit hard to tell from the way these pictures are framed, but like the batter stances are somewhat different. They're clearly different players. I actually forgot who each of them were, but one of them might be a power hitter and the other might not. So maybe the umpire's got some bias that maybe one batter's known for laying off of pitches and the other one isn't. So maybe something about the batter is there. What else do we see that's different? Yeah. Yep. Yeah. So that's exactly this idea of framing. So what happened during the game is that if you were watching the broadcast, and this was, kind of just getting to the start of like tweeting while you're watching baseball. So like people on Twitter were sort of railing about this umpire is super biased. He's calling a super permissive strike zone for the Astros, and he's calling nothing for the Yankees. So this was like concentrated in New York, were the people saying that. But the commentators, when they were watching the game, they started talking about this as well. And they started saying that, oh, this catcher, this is Hank Conger, who is the catcher for the Astros. He's known as being a great pitch frame. He's really sort of influencing the umpire. He's sort of operating at elite levels of pitch framing, and that's what's driving the difference. And this was brought up during the telecast. They were talking about this skill, about how the catcher is catching a couple of baseballs every game, and saying this is the reason that the Yankees were facing a very aggressive strike zone, whereas the Astros did not have such an aggressive strike zone because their catcher is not as good as framing. And so this was brought up in the game. And this leads to the question, is it really the catcher or is it any of the other things that you all mentioned? The handedness of the pitcher, the players. These were pitches thrown in very different contexts. I think one was thrown with 2 outs and nobody on. One is thrown with no outs and somebody on second. One was in the top of the third. The other's the bottom of the fifth. So we got all these differences. So was it really the catcher or is it any of the other things? And so what this gets at is this idea of pitch framing. And this was a thing that was talked about a decade ago as kind of the next big thing in baseball analytics. And broadly, you'll find a lot of definitions for pitch framing, but I think the best one is it's the ability of the catcher to affect the likelihood that a pitch is called a ball or a strike. This could manifest, or the mechanism could be done in many ways. It could be how they actually receive it, whether they break out of their stance. It could be just reputational, but we're not going to worry about kind of the mechanism. We just want to know that if it's a thing that's happening, we should be able to see it in data. So we're going to frame it as the ability of a catcher to affect the probability that an umpire calls any pitch a ball or a strike. And you'll hear it talked about as they make balls look like strikes, or sometimes they'll say an elite pitch framer is good at stealing strikes, turning balls into strikes. And there was, I guess it's topical because it was about a Brewers player back in the day. There was a great ESPN The Magazine feature back in 2014 about Jonathan LaCroix, who spent a couple of seasons here. And they estimated that, and I think the real pull quote here was, they said, framing is this huge thing. LaCroix's really good at it. And he's the most impactful player in baseball, and he's the 17th highest paid catcher. If you read through that article, they're basically saying that, he's got like 18 wins just by his ability to turn a ball into a strike. And that's like an outsized value. That's like the best hitters in the game don't even come close to this. And so by kind of standard conversions from earned runs to wins above replacements to dollar values, there's some conventional heuristics people use. They would say that on the free agent market, this skill is worth like $14 million a year. So that was kind of interesting. And I was a student during this time, and we saw this, and we keep reading. And so there's Hank Conger, who was the Astros catcher back in that picture. They're saying that, his wins above replacement just by his batting and other metrics of his, catcher defense was like 0.7. And his framing alone was like two and a half, almost 3 wins above replacement. That's crazy, right? There's no way this effect could be that big. And so this is how the project started. I had a professor walked in. We were in a department that had this very nice culture of the students and faculty ate lunch together. I had this professor who could be known to bloviate a little bit, walks in and said, "You won't believe what I saw last night." He's a big Yankees fan, so he was pretty in his feelings that day after they lost. He said, "I can't believe it. This framing thing, I've been doing my research," pulls this up, says, "There's no way this effect is this big." And I said, "That sounds kind of interesting." He's like, "Let's figure it out." So that's how this project started, was my professor getting angry, like yelling at the TV, and then here I am. So what a weird trip it's been. So the questions we're going to ask: what pitches are frameable? So at least intuitively, we believe if the pitch is thrown straight over home plate, right down the middle, doesn't matter who the catcher is, doesn't matter who the batter is. Maybe it matters who the umpire is. There's some who really just can't even call that right. But leaving that aside, there's some pitches that just aren't frameable. If you totally miss the batter, you throw behind the batter, there's no chance that that's going to be called a strike. So not every pitch is frameable. So now we're thinking about this huge outsized skill that manifests only on a small subset of pitches. And it's this massive contribution to wins over replacement. So let's try to figure out which pitches are actually frameable. The other thing is, as soon as we start assigning dollar values to this and teams are starting to make roster decisions, maybe we believe that the $14 million is sort of the right, estimate of the effect. Like that's how much the market should pay for this skill. Is it like plus or minus 20 million? Or is it like plus or minus 10K? Like what's the actual uncertainty here? Because if I need to make a decision about who to roster and how much to pay them, I really want to know if it's this, then I think it'd be much easier to convince an owner to fork over 14 million. But if it's this, there's no way. If I'm uncertain about the value of this skill, there's no way that that team should be paying for it. And then finally, there's a question that sort of is alluded underneath this poll, which is framing stable season to season? But players very good at pitch framing in one season, are they good again? And this gets to like kind of the perennial question in sports analytics is, am I measuring a skill? Because the skill is something that should be repeatable year over year. That's something that's worth investing in. But if it's just noise, if it's, I might be a good framer this year and I'm not a good framer the next year, even accounting for some regression to the mean, then I certainly am not going to want to pay for that. So these were the questions we wanted to answer. And so this is really where kind of our kind of statistics starts to get in there. Like, how are we going to even quantify this? So let's start by examining the premise, right? There's this premise that framing is somehow a good thing for a defense, for a pitching team, and that getting a ball is worse than getting a strike. And so we kind of believe from like a resource allocation thing, kind of framework, that we can convince ourselves that you want to get more strikes and fewer balls. But we can actually quantify this because, you know, you'll see that they talk about this in terms of wins above replacement. And in baseball, we typically use one of two different kind of measures, or sort of currencies, if you will, about measuring skills. It's either wins above replacement or kind of expected runs. So we might ask, how many more runs is a team going to give up in the rest of the half inning, you know, before the reset in the game? And so that's kind of the unit that we're going to work with. Not wins, not win probability, not some other kind of statistic somebody dreamed up. We're going to use expected runs. So we're always going to try to understand these skills in terms of some units. And there's a nice conversion from wins above replacements to expected runs. It's about 10. So at a replacement, you know, one extra win, and it corresponds to about 10 extra runs is the usual conversion. So we're going to frame everything in terms of expected runs. So what is the value of just turning a ball into a strike? And so just by kind of a poll here, how many of you think it's sort of constant depending on the game state? Is a strike in an empty count worth the same as a strike in a full count? I see some folks saying yes. I see some heads shaking. Why are you?
Part of the strategy of baseball is pitch count.
Okay.
So one of the strikes, pitch count,
Okay.
your mid, Bader,
Uh-huh.
possibly then score closer.
Yep.
Because then gives you an advantage. That's
Okay. You don't agree?
No, I do.
Oh, okay. Well, I don't. So no, so the idea is like, what is a strike worth? So what we did was we said, okay, let's actually see what's borne out in the data. So we went and looked at all of the pitches thrown over, I guess this was like a 10-year period. So I wrote this paper in 2017, and then I've sort of updated it a few times. So I'm giving you kind of the new results. So we looked 2008 to 2018, and we asked a really simple question. We're going to look at a game where a batter takes a pitch. So there's going to be a call. And we're going to see on, like, say, a 2-0 with nobody out, how many runs does the fielding team give up after that situation and a called ball? And how many runs are given up after a called strike? And so when you look at the difference there, that gives us a sense of how much would sort of the different call be worth. So as an example, in a 1-1 with one out, the fielding team gives up about a half run after a ball. We looked at all of those situations over these 10 years. We found that on average, the fielding team sort of gives up half a run. After a strike, they give up about 0.3536 runs. And so we value called strike here saves about 0.14 runs on average. And you'll notice that all of the numbers here are positive. So it's saying, like, no matter the situation, a strike is better than a ball, right? You're very rarely going to, at least in terms of earned runs. Now, there might be other strategic reasons to want to have a ball. Maybe, you want to sort of pitch out to somebody. That's all fine. We're working on the unit of runs saved or earned runs saved. If you change the unit, things will obviously change. So that's going to be something we have to keep in mind. Okay, great. So this at least convinces us that this is maybe why people think framing is such a good skill, because you're somehow saving your team runs. Because you're taking what would have been a ball, turning it into a strike, and therefore moving the game to a state where you're giving up fewer runs. So this is why we might think that being able to turn balls into strikes is good. Okay, so how do we relate this to framing and valuing framing? Probably the simplest idea would be to say, okay, given a game state, maybe the number of outs, the base runner configuration, the inning, whether you're the top or the bottom, like we can take this table, right? I've laid it out in 2 dimensions. We can add a whole bunch of other things. We could do this by the combination of count, outs, and the who's on and who's not. We can sort of do the same type of calculation. The results don't really change that much. But the idea is that given the game context, we could say, let me find out the value of a strike in this context. And okay, if it's a called strike, I'll give that catcher some amount of credit, some like row, whatever that value was. And if they get a ball, I'll subtract that. So I'll give the catcher credit for a strike and blame for a ball. And I'll weight it because, a strike or a ball in different contexts means sort of has different value. And then we would just sum this reward for all pitches that were received. And that would be kind of the end of the day. And this is what a lot of the early framing things did. They would call it something, if you sort of read a lot of fan graphs, it would be, I think, extra strikes is what they used to call it for a while. Just these ideas that, hey, you got a strike, you got a ball. If you get a strike, you get some positive credits. If you get a ball, you get some negative credits. And it's a very simple thing to compute. You don't need any sort of fancy machine learning to do it. But if you stare at it a little bit, it assigns all of the credit to the catcher or all of the blame to the catcher. So if the pitch is thrown straight down the middle, doesn't matter who's catching it. If I was catching it, it would still be a strike. That doesn't seem very fair. Right? Like that doesn't really mean anything. I didn't do anything. Or if the pitcher completely misses the sort of a wild pitch, why should I get the blame? It's the pitcher's fault. I mean, we can argue the semantics of that, but like let's take it from the catcher's perspective. And other sort of assumes that all pitches are frameable, which we know they're not. And so what we're going to want to do is we're going to want to try to tease apart when can we assign credit to the catcher. And so this took us a while, but here's the idea. Now, this looks like kind of a weird formula, so let me walk through it. The idea is that, let's say, I could look at the context of the pitch, and I told you where it's going to cross home plate. So if you looked in that sort of plane above home plate, where is the pitch located? Right when it crosses the front edge of home plate. That is what the umpire is supposed to be basing their decision. I tell you that location, I tell you all the other information about the pitch, and you have an oracle or some machine that tells you exactly what the probability is that the umpire is going to call it a strike. And I can tell you that for any combination of players or pitch locations. Let's say we have this estimate. So we're going to call that P. For a particular play, I will look and come up with what's the chance that the umpire is going to call this pitch a strike. Then I can ask, what if we had used a league average catcher? Kept everything else the same. Or instead of a league average catcher, what if we did the thought experiment of having every catcher in the game cycle through that one pitch, and we could somehow simulate what would have happened had they been the one to receive it? So obviously it's a little bit of a weird thought experiment because, catchers don't switch teams in the middle of a game, but let's say they did. For every catcher, I would know what the chances of a strike was going to be. I mean, this is a positivity violation, so don't yell at me, but this is what we did. It's the idea that if I'm somehow very good at framing and nobody else is, then somehow my probability should be much higher than everybody else's. Because it's me who has the skill. And so if you put anybody else in, that probability of getting a strike instead of a ball should go down. So the idea is that by looking at the difference between the actual called strike probability for a particular catcher on that play and this kind of league average baseline, that actually captures the catcher-specific contribution to the probability that a pitch is called a strike or not. So that's really the framing effect. And now we can weight it by the value. So if you get a strike in a high leverage situation, you should get a little bit more credit, but you should only get that credit if nobody else would have been able to frame it. Or like the league average was not going to be able to frame it. So this is going to automatically adjust for those situations where I throw a pitch straight down the middle, doesn't matter who it is catching it, then these two probabilities are going to be pretty much the same. It'll be close to zero. So you're not going to pick up any credit for framing that pitch because it wasn't frameable. The frameable pitches are the ones where this probability minus the baseline probability is big. Or if you're really bad at, catching or framing, then maybe this is negative. That can happen too. You're worse than the league average at, turning balls into strikes. Well, that will show up as well. So this is correctly solved. So this is kind of what we wanted to do. Is okay, if I could tell you the probability, given the player configuration, given all the players, the game state, everything else, the umpire, if I could just plug that into a machine to give me the catcher's probability of getting that strike and the league average probability of getting that strike, then I could just run this computation and call it. Now, of course, the elephant in the room is we don't know these exactly. Nobody's going to hand this probability to us. I have to estimate it, and there's going to be uncertainty. And so uncertainty about this probability, uncertainty about this baseline probability is going to reduce uncertainty in their difference. This could be maybe between 40 and 60%. This could be between, say, 20 and 30%. So the difference could be over this kind of wide range. And the uncertainty here is going to drive uncertainty into the actual value. I'm summing it up. I'm going to have to think about, tracking these uncertainties really carefully. And so I don't want to go into all of the technical details, but the reason that we took what's known as a Bayesian approach here is that it makes this uncertainty quantification really easy. And we can talk about all of that later on, but it was sort of important for this problem because we ultimately wanted to take this. This is on the scale of earned runs. We can convert that to a dollar amount. So if I can put an interval over this, then I can turn that into that 14 million plus or minus whatever, right? The error. So this is all I needed to do. And I just need to be able to estimate these called strike probabilities. So we've gone from this question of, how much is framing worth really to a concrete statistical problem. I just need to estimate called strike probabilities. And as soon as I can do that, I can go through this calculation and estimate the value of framing and do this for every single catcher. So, called strike probabilities. At the most general level, the probability that you get a called strike on any given pitch is obviously going to depend on pitch location. Like that is the main driver, just like in real estate, right? It's location, location, location. But the personnel also matters. There were some umpires that got flagged in our analysis for being really susceptible to framing and just making bad calls. And it's been one of the joys of my career to see over the years, seeing them sort of dragged mercilessly online after really bad performances. If you're familiar with Angel Hernandez, he's a real star of the paper. His first base calls are different, but so the personnel matters. The context also matters. There's some psychology that says, hey, it's getting close to the end of the game. The score is pretty wildly out of margin. Like the game's basically over, but we still got to grind through the 8th and the 9th inning. Umpires probably want to go home, so they might call some strikes. Like that actually can happen. So we got to account for context. And so if you've ever taken a statistics class, you'll know that this is pretty hard. Like I've got interactions. How am I going to parameterize locations? What is the actual form of this model? And that's where we need to start doing some actual modeling and some statistics. So the goal is I got to estimate called strike probabilities. And I don't want to make too many assumptions about what this function looks like. At the end of the day, I just want to have it. I want to plug in kind of the location of the pitch, the personnel involved, the game context, and I want to spit out a number and maybe an interval for what the called strike probability is, what is the uncertainty, and then I'll run it through this kind of rebalancing against the baseline and reweighting by the value, and then rolling up those to get an aggregate. So I'll spend maybe 5 minutes going through the actual way we did this. So if you don't love statistics, that's fine. I'll keep it brief, but I at least want to motivate the general modeling approach. And so the data is coming to us from PitchFX and StatCast. So we've got pitch tracking data. We have essentially the whole trajectory of the pitch from the moment it leaves the pitcher's hand to the time it gets received by the catcher or makes contact with the bat. We have about 350,000 called strikes or called pitches every season. This is pretty stable season to season, give or take 5,000. And every season we have about 1,000 batters, about 700 to 800 pitchers, about 100 catchers, and about 100 umpires. So we got a lot of data here. And what we're going to pull out of these data is the location of the pitch as it crosses kind of the front edge of home plate. Something we're not going to use is where the PitchFX operator sets the strike zone. So we're not going to use any information of whether MLB thinks it's a ball or a strike. Because actually what happens with PitchFX is they used to have a camera operator who would aim one camera right at the batter's chest and another at the batter's knee. And sometimes they weren't very good at that. So you'll get some players whose strike zones are bigger than them. So we're going to throw that bit of data out. So this is what we have. We got to use the location and the identities of the people involved and some of the contextual information, the count, the number of outs, whether you're in the top or the bottom, to estimate call strike probabilities. And so if you've taken like a stat 101 type of thing, you'll say, right, this is a binary classification problem. I'm predicting a 1-0 and I want a probability. So I'll use logistic regression. This is kind of the canonical workhorse of applied statistics. The formula looks crazy, but I promise it's not. Instead of working with the probability, a called strike, we work with what's known as the log odds. Probabilities are between 0 and 1. Log odds can take any value. It just turns out to be much easier to operate on that scale. We just take the probability of a strike divided by the probability of the ball, and then sort of transform it in a way. And what we're going to say, and we want to bake in a lot of prior knowledge that we know pitches thrown straight down the middle are probably strikes. We would like to incorporate that. We don't want the model to discover that on its own, right? We know that kind of mechanistically should happen. So we want to build in some of that prior knowledge. And the way we did it back when I was a student was we actually looked up another paper, which was studying a totally different problem, but had built this kind of nice model for, you give me the location of a pitch, but don't tell me anything else, and I'll output the probability of a called strike. So we had this kind of baseline probability based on data from seasons before we were looking. So we kind of had like a historical baseline. So we said, right, I would like the probability of a called strike should at least be similar to a historical baseline. It doesn't change that much. 2016, they moved the strike zone down. But apart from that, it should be pretty similar. So we took this historical estimate and we transformed it in the same way. So we had this p hat, which was that historical estimate. We log-ogged it, and then we just threw it in as a predictor. So that what's saying here is that in a particular season, say 2017, the log odds of getting a called strike is essentially the historical log odds plus a bunch of offsets. An offset for the umpire, an offset for the catcher, an offset for the batter, an offset for the the count, and who did I leave out? The pitcher, yeah, all of the players involved. Just some additive offsets. So if we thought that this is signed in a way where positive values are going to increase the probability of a called strike, and negative values are going to decrease the probability of a called strike. So what we have is a parameter for every player, every batter, every catcher, every pitcher, every umpire, every count that we need to estimate from these data. So we've got about 2,000 parameters. All like every batter has a number. That's kind of, you take the historical log odds and you offset them by something specific to the batter, and then that will give you kind of their contribution, the probability of a called strike. So this is not the hardest problem. We've got way more data than the number of unknowns. So this is a well-posed statistical problem. The problem with this model, what we found, is that it's not flexible enough. It assumes that every player affects every umpire in exactly the same way. It assumes that every player impacts the log odds of a called strike at every location in exactly the same way. And so when we ran this by some folks that we knew at some teams, they said, no, we know that our guy is really good at framing on the outside corner, but he's really bad at framing on the inside corner. Bake that into your model. And I said, great, I'm the grad student. I guess I have to figure this one out. So this gets us to the summer of 2015 and 16. And so really this is about player and location effects. Are they really the same? So we're going to need something a little bit more flexible. And so the next version of the model was, well, I care about each individual umpire's decision, and I know umpires are different. So why don't I just build the exact same model, but subset it to every umpire's data? Right? So if I'm Angel Hernandez, I'm going to take all of the pitches that he's called, fit that model. If I'm another umpire, I'll fit a model to that. Because I know umpires are different. Maybe a player is very good at fooling one umpire, but not so much another. Let me bake that into a model. So all I did was I took the model from the last slide, and I just added a U. And so formally what this is doing is it's saying, instead of fitting one big model, I'm going to fit a bunch of little ones, one for every umpire. And I'm going to try to understand every player's effect on every single umpire. This is pretty ambitious, but it acknowledges there's umpire to umpire variability. Here's the problem. First, umpires, they are different, but they're also kind of the same. for the most part. The other more sort of technical thing is that we still have like 2,000 parameters per umpire. I want to know the effect of every batter on every umpire, right? I got to know 1,000 effects for every umpire just for the batters. Well, I only have about 2,500 to 3,000 pitches per umpire, right? I've got 350 total thousand, and then 100 umpires, so about 2,500 to 3,500 per umpire. And now we're in a setting where the number of data points is about equal to the number of unknown observations, and that's a problem. So we're gonna have to do a bit of work there. And the more serious thing is that not every player appears before every umpire. Right? There's a fixed number of games in a season. You don't cycle through all the umpires. So some of these effects are just not even defined. They're not even estimable from data. So what do we do there? Because I want to be able to predict how might a new catcher have fared in a particular situation if I've never seen them perform in front of that umpire before. So this sort of separate umpire modeling has got its issues. Like, yes, we captured umpire to umpire variability, but we've opened up a whole other can of worms. So we've got these two extremes. One model that kind of assumes all the umpires are the same, another model that assumes they're different, and they both have problems. And so the happy medium between them is to use a technique that's known as partial pool. And this is kind of the hallmark of hierarchical Bayesian modeling and sort of the types of modeling that I do. And it's a way to kind of systematically say, I know that there's similarities across groups in my data, but I know that there's differences across those groups. And I'd like the data to kind of automatically interpolate between them. Like when there's similarities, leverage those similarities, but allow them to still be different. So formally what we'll do is it's the same model as before. I have a catcher effect on every umpire. But what I'm going to make sure that I estimate in a way such that catcher C's effect on umpire U is sort of pulled towards the overall average effect of all catchers on that particular umpire. So even if I haven't seen catcher C appear with you before, I'll say that he's probably close to the average. So I'm going to pull them somewhat close to the average, and how much I pull them close to the average is determined by the data. Then what I'll say is that, okay, now I have this sort of catcher-specific average for every umpire. Across umpires, now let me pull those average values to a global mean. So we're kind of building dependencies in and saying, although we don't have data for this specific situation, can I leverage similar situations to give me an informed estimate? So it's kind of solving this missing data problem of I haven't seen certain player-umpire combinations. I'm going to allow data that's from a similar context to kind of borrow strength and inform the estimation. And this is kind of the hallmark of hierarchical modeling. And that's the end of the technical bits. The rest is all kind of fun pictures. So the point is we really had to think hard about building that called strike model because we want to be able to predict these counterfactuals. How will a player perform in a particular situation when we swap them out with one other player? So we need those estimates and we need them to be reliable. So we built these models. About 10 years ago, this was an exercise that took about, I don't know, like a week on a supercomputer to grind through the calculations. We've got it down to like a few hours. So now teams can start using the model. Before they would call us and say, we'd like to implement your model. And I said, do you have a supercomputer? I said, no. I said, too bad. So here's what we got. So this is 2009, the same sort of computation. And what I'm plotting here is I computed that probability for every strike. For every called pitch, I computed the called strike probability. I computed the league average baseline. I looked at the difference. I weighted it based on the value of a strike in that situation. And I added it up for every catcher. So you had 1,000 pitches that you received in a year. I added up 1,000 of those little contributions. And we got to how many runs did you save? I was able to track the uncertainties. So these bars are sort of 95% uncertainty intervals. So I may not know the value exactly, but I'm pretty damn sure it's somewhere within those bars. These aren't confidence intervals. They're something slightly different. And what we saw in 2009 is, boy, there's somebody who saved about 50 runs, plus or minus like 10 or 12. So just to convert this back to dollars, 10 runs is one win. One win is $7 million. So we're looking at like some valuation plus or minus 7 million. Not nothing. But then we have kind of a vast middle here where people basically did not much better than baseline. And we've got some catchers here who maybe materially made things worse for their teams, which is not great. So this we could get these sort of pictures for every season. But I think the real question, so we were pretty satisfied that looking at this type of analysis, we could identify the frameable pitches, and in any given season, we could say, how much do we think it was worth? And we could put an error bar around it. And so we were pretty satisfied with those answers. And we looked at the players who were involved, and they kind of made sense based on what kind of the sabermetrics community was saying, how teams were valuing these players. You know, Tampa Bay was early to pitch framing, and you could see who they were paying and when, and kind of tracked with these results. But I mentioned earlier that kind of an important problem is, like, this is 2009. What happened the next year? And if I'm investing in this from the team's perspective, I really want to be paying not for past performance, but for like future performance. So here's the plot. So we looked 2009 to 2019, same type of analysis. And what's happening here is for every kind of dot is a particular catcher year, and I'm connecting each catcher across seasons. And I've highlighted 4 catchers who, over this decade, they were, you know, at times considered really elite pitch framers. So Jonathan LaCroix, who I mentioned at the very beginning, he shows up as pretty good in 2011 and 2014. He's sort of the best framer in the game, and that sort of tracks when ESPN was talking about that. So that was kind of nice to see popping out of our data. And then he falls off a cliff. And it was funny, a few years after our paper came out, somebody sent me this piece by Ben Lindbergh in The Ringer, which is like, 3,000 words about how the best framer in baseball suddenly lost his ability to frame pitches. And that's exactly what we see. He was amongst the worst in baseball in 2017. So that's kind of nice to see our data is, passing the eye test, or our analysis is passing the eye test. And so I kind of hinted at why this might have been. And it took us a while. But when this paper came out, this was when they started talking about the robot umpire and rolling that in. And like, that's never going to happen. The umpires union will basically never let that happen. But one of the things that they agreed to back in 2009 was they're reviewed at the end of each season. So umpires receive a grade from the league. And so you can at least plausibly tell a story for why do we see this decline. It's not that catchers who were good at framing in one year suddenly forget how to do it. But there's at least a mechanistic reason that we see such a dramatic decline in perceived value. It's because umpires have their calls reviewed every single season, and there's league-wide guidance about how they should be calling the strike zone. In about 2016, there was sort of guidance that you've got to drop it a little bit, and you would see that actually manifesting. And so on the basis of this, our conclusion was, there's a lot of uncertainty in the huge impact that framing has. The dollar amounts are on the same scale of millions of dollars, plus or minus one win. That's a lot for a small scale. Now, obviously, you're evaluating players holistically. You care about their defense. You care about their batting. But if you're going to sign a huge contract based on framing alone, the results from our paper really said, don't do it. And then I think another reason is because it's not really stable season to season, because there's a sort of non-stationary effect of if you get a reputation of being very good at framing pitches, umpires are going to call you a little bit tighter the next year. Nobody likes to be told somebody pulled one over you and sort of fooled you into making the wrong call. So there's at least a mechanistic reason why we don't expect it to be stable to this over seasons. And then over the years, we've kind of improved the called strike estimates. One of the big ones that we're thinking about now is umpires don't make ball strike decisions based on where the ball is the moment it crosses the front edge of home plate. They're watching how the ball moves in. And I think somebody mentioned earlier about the left-handed and right-handed pitcher. You can see the trajectory of the ball. So somehow designing statistical methods that actually leverage the full trajectory of a pitch as it's coming to home plate. Can we identify when umpires have made their decision? So that's kind of kicking around in the back of our heads. And I know I see at least one other causal researcher here. There's a massive confounding issue in that what we did was we just computed the probability of a called strike and then made up this counterfactual of what if you just replace the catcher with every other one or a league average? There's an issue that catchers are paired with pitchers, and some pitchers are just much better at command. And so how much of this is really attributable to the catcher versus their platoon mate who maybe isn't very good at painting the edges? And so there is a certain amount of confounding that we have to adjust. So anybody interested in causal inference, I think sports offers a pretty fun and exciting place to try stuff out, and new identification and all sorts of causal inference can be done. And so I wanted to leave with, this was kind of a case study of how we started with our problem and worked our way through like a statistical solution. We didn't start the project by saying, I got a bunch of data, let me fit a model and then try to dress it up. We really had to start with a question. What is it that we wanted to know? And this has really been a through line through a lot of our work. So I'll highlight three papers. The first is with a dear friend, Kathy Evans, who is now, I think, the first 3-sport analyst. She's working with teams across 3 different sports. So, she's like the Deion Sanders, if you will. She and I worked on something where we were, thinking about, if you've watched, any of Amazon's like football broadcasts, you'll see AWS will have that graphic of, hey, as the ball is in the air, the probability of the catch is like going from 0 to like 100% or like that. So we got really annoyed by that because they were rolling this out in 2019. So we said, can we just build that ourselves? And I don't care about the probability of the completion on the targeted receiver. I want to know, what if they had thrown to somebody else? Like, was there a better throw that was available? And so we really tried to start from that question of, are quarterbacks throwing to the most open receiver? Are they making the best decision? Is that actually the best read if all I care about is getting a completion? Now, you can do this for if all I care about is a touchdown or a first down, but at least for completions, we found some really interesting things. With Ryan Brill and Adi Weiner over at Penn, we really tried to look through the third time through the order penalty, this idea that the third time a batter sees a pitcher, they somehow just do so much better. That doesn't turn out to be the case. So we really had to think about how we model that and deal with some of the data issues there. And most recently with one of my PhD students, we wanted to know, are batters good at deciding when they lay off of pitches? And so we had to build up a framework of how do we even quantify what good is and how do we model each part of the decision-making process? And what we found is, like, for the most part, major league batters are pretty good at this, but there is variability. That variability is quite large. And so that's kind of this idea of thinking about decision-making and how do we even evaluate, are players making good decisions and how we might change those decisions. So it's a big theme of some of the research. I've got some other ongoing projects all happening here with our colleague in CS. We're thinking about the in-game win probabilities, not so much because we want to bet in games, but we're kind of, the standard for win probabilities is they'll look at a game state and say, from this game state forward, how often do people win and how often do people lose? And so you'll see in football, fourth down decisions are often made by consulting kind of a big win probability matrix. And I always find that problematic because if I know that my team hasn't been able to run the ball at all, that should somehow factor into this. I shouldn't throw out the historical information of how I got to a state in a game. Should inform where I think the game is going. It's not Markovian. It doesn't matter. I can't just ignore history. So with Josiah, we're really thinking about how do we roll history in the game and past performance into our forecasts of what will come next. With a student, Paul and Jamie, who's over at Tufts, he's an athletic trainer. We're interested in the decathlon because it's sort of the hardest sport in some sense. You've got to be good at speed and strength and endurance. And we're really interested in understanding when performance peaks in the decathlon. We know for the 100 meters, there's sort of an age curve, and it's pretty well understood when performance in the 100 meters sort of peaks, but that isn't the same as performance in the javelin or performance in the shot put or performance in the hurdles. And so we're really trying to understand, we were watching the Olympics together and we asked, like, how close are we to seeing the highest possible decathlon score? And when might we see that? And at what age might that be accomplishable? So Paul's got some really cool results there. And something that we've been spinning up here with Keith and Dan is really trying to individualize recovery curves coming off of injuries. And that's with with another student of mine. So that's pretty nascent, but we're already seeing some pretty interesting results there. And I'll say I got a couple of blue sky projects. There's a lot of tracking data floating around. And as much as it's as cool as it is to know where athletes are, 10 times a second on the field, what the hell do I do with that? How do I connect that to a winning play or a winning decision? And also, during practice, there's a lot of performance and training data that's getting collected. What do we do with this? It's not enough just to collect that data. You can't stare at it for all day and just see something that pops out. It's like, oh, this is now my competitive advantage. It has to start from a question. It has to be well defined, and it has to, in my opinion, be framed statistically. So I know I'm really running up against the time. So thank you all. Feel free to get in touch. If you're interested in the paper, the preprint's up there. It's in a journal, but I don't know if it's open access or not. So get the preprint. Don't go to the publishers. And with that, thanks.
Samir, if we take that question.
Absolutely.
They want to have a question.
I do.
Yeah.
So in this, I don't really know anything about major leagues,
Sounds good.
but can pitches be overturned? So like a lot of the times you have video review or things like that,
Nope.
but as soon as they're called, it's called.
Whatever God's lips to the umpire, I guess. Yeah, the umpire's decision is basically fine.
Okay. I didn't know if that would then if
At least
so.
for ball strikes. I guess for check swings, there is at least a mechanism to check that, but they really don't review them.
So that wouldn't.
What? It's pretty extreme, pretty rare.
Samir, I was thinking of like other sports, how and whether you take insights from something like this, like a subtle thing like pitch framing to other sports. So I was thinking of this basketball player for the New York Knicks, Jalen Brunson, who's a great player, but he's got this specialty skill set of drawing fouls, where he's really, really good at making these subtle little moves to draw fouls. And but it's like a really hard thing to measure or understand, like in different ways. Are there ways of taking some things you learned here methodologically about other sports, things like that? Or is it starting from scratch every time to think about how you would learn about it?
I think it's a little bit of both. So in that one specific instance, I think you're on the way to actually asking the question. But I still think like a lot of work has to be done. And, if you're going to use data to try to answer it, it's got to be a quantitative question. So is Jalen Brunson sort of picking up, getting more fouls than you would have expected from a similar play? So that if you ask it like that, then we can start to ask, okay, who's similar to him? And you would then have to define kind of what you mean by similar, how similar they are, and are their usages similar? And that starts getting towards that. The specific modeling, maybe, but then you have to start asking, hey, there was a thing that Jalen Brunson did, and you have to be able to see both sides, right? You can't just look at all of his foul calls. You have to see the non-foul calls as well. And baseball's super discrete, so it's very easy to define these things. In basketball, you have to start making a couple of decisions. And obviously your analysis is going to be sensitive to that, but that's not a problem necessarily. You just have to be very clear about how you're defining things and sort of constraining the scope. So asking like about this very subtle skill that he has, the actual question you'll end up answering is kind of a version of it. And so you'll have to narrow it a bit. But I think some of these are the same ideas, thinking about what would another player have done. Otherwise, if everybody is going to get that foul call, then it's really not specific to the player, right? Yeah.
Just for one last question.
Oh.
So the formula like not for like the difficulty of the pitch to frame it. It's like as I was saying, the location be completely different if it's that 4 inches of run coming in or 4 inches of run going out. Also, like talk about different situations with batter, it's a lot easier to maybe frame a high pitch against Aaron Judge 6'7" versus Jose Altuve, he's 5'6"? Like, did it account for because that difficulty of the framing can account for the value
Yeah.
of war?
Yeah. The short answer is no. And when we rolled this out for the first time, we just didn't have a good way to put that into the model. Now we're using to estimate, strike probabilities. We're using a much more flexible framework, sort of a machine learning tool. That's kind of the basis of a lot of my methods research. That allows you to start throwing more variables into this. Go crazy with what you want to put into the model and adjusting for. It's able to kind of sift through it and pick out the right ones. And so, although we didn't include those variables, largely because we didn't have them, the framework now exists so that we could put them in if we wanted. The results will change. The model's only as good as what you can put into it. So if you put better things in, you'll sort of get more refined answers, but then it's just turning the crank and sort of redoing the calculations with kind of the better strike probability things and getting that sort of how the pitch is breaking. When we did this for the first time, we didn't actually get a good measurement of break. Now with StatCast and with the new camera technology, we have much better kind of granular pitch data about the ball's movement. So it would be interesting to kind of redo this with better break measurements and that full trajectory.
Want to definitely thank Samir for a really interesting project. Before you leave, anyone who's interested in getting a picture with our group, we'd love to start capturing these a little bit. So we'll come up to the front, get a picture behind Samir, our expert. Anyone who wants to be in, we'll put that on our social media.
Certainly not behind, just sort of
all who want to be a part of it, please join. Otherwise, just thank you, Samir, and thank you, everybody.